Welcome to SpaceTime with Stuart Gary.
Scientists have developed a new way of understanding how stars like our Sun evolve. The new research, reported in the monthly notices of the Royal Astronomical Society, is the first attempt to build a comprehensive model for the activity and evolution of these Sun-like stars. The study's lead author, Professor Eric Blackman from the University of Rochester, says the work could ultimately help determine the age of stars far more precisely than existing models. The authors combine data from a multitude of Sun-like stars, looking at the physics behind changes in the star's rotation rate, its X-ray emissions, magnetic field generation, and the intensity of its stellar winds, in other words, how quickly it lost mass. The Sun is a typical main sequence spectral type G yellow dwarf star, approximately 4.6 billion years old. The Sun has a mass of about 1.98855 times 10 to the 30 kilograms. That's about 333,000 times the mass of the Earth. The Sun's also about 1,300,000 times the volume of the Earth and has a diameter of 695,700 kilometers, some 109 times that of Earth. The Sun's luminosity is 3.828 times 10 to the 28 watts, with a surface temperature of about 5,800 degrees Kelvin and a core temperature of about 15 million degrees Kelvin. Our Sun is expected to keep shining on the main sequence all up for some 12 billion years. It'll then expand into a red giant, and after puffing off its outer envelope, it'll end its life slowly cooling as a white dwarf. Using our Sun as a calibration point, the new model developed by Blackman and colleagues most accurately describes the likely behaviour of the Sun in the past and how it's expected to behave into the future. And as there are lots of stars of similar mass and radius to our Sun, this new model provides a good starting point for predictions about these other stars as well. The model shows that stars younger than the Sun can vary quite significantly in the intensity of their X-rays and their rate of mass loss. However, there appears to be a convergence in the activity of stars after a certain age. It seems they get more predictable as they get older. Astronomers aren't yet at the point where they can accurately predict a star's precise age. That's because there are simplifying assumptions going into the model. But in principle, by extending the work to relax some of these assumptions, astronomers could theoretically predict the age of a wide range of stars based on their X-ray luminosity. At the moment, empirically determining the age of stars is most easily accomplished if the star's among a cluster of other stars, from whose mutual characteristics astronomers can estimate the age. At the moment, a stellar age can only be estimated to an accuracy of about 25%. The problem's worse for field stars alone in space because the cluster dating method can't be used. For these stars, astronomers use gyrochronology and activity aging. Basically, it means older stars rotate more slowly and have lower X-ray luminosities than younger stars. In recent decades, astronomers have empirically measured these trends in rotation and magnetic activity for stars like the Sun. Ultimately, this could well lead to improved constraints on the evolution of rotation and activity in Sun-like stars, and better constraints on how the magnetic characteristics of the Sun have changed over the course of its main sequence life. And this is really where the new model is important. It provides a physics explanation for how stellar rotation, activity, magnetic field and mass loss all mutually evolve with age.